as I said, basically we will be continuing forward. So in the last class, basically we discussed about model fitting methods. So the idea was basically we have a lot of feature points, and we want to basically fit all those data points to a particular model. It can be a simple straight line, circle, or it can be some kind of for matching images. We may have to do a transformation matrix, so we have to fit a transformation matrix on that data and so on. So how to do that? Because in the real world scenario, we will have a lot of noise and outliers and noisy situations. Some points may be just random noise points. Some points may be missing. Some points may be displaced not at the proper positions and so on. So we started with a very simple least square method of algebraic method of basically fitting a line, and which is kind of a global optimization method. So it takes all the data points and tries to do a least square fit to find the best fit line. And in order to little bit accommodate noise, we saw some robust least square fit method for that purpose. But it had a lot of problems we had seen, because first of all it can only fit one line at a time. So if there are multiple lines in the data point in the image, we'll have to it cannot fit them all of them in one go. So we'll have to use some more things to do that. And also it was not so robust to noise. It was a little difficult to basically make it robust. So today we are going to discuss a more general method called voting, and there are two variants of this which are very popular methods in computer vision, which are used for fitting data points to different models. And sometimes Houghtransform is used for a particular purpose and ransack is used for other purpose. Each has its pros and cons, so we'll discuss them. So let me know, you feel free to pause and ask questions if you are not able to understand anything at some point of time. So that is the benefit of doing a live class instead of recorded video. So so we had we had already explained that what is the problem basically in model fitting. The problem is the data points are too many, and it is not possible to check all possible models or all combination of features by fitting a model to each possible subset. So what it basically means, let us say there are n points, so and so and there can be n C2 combinations of 2 points, and because the line can be defined by just 2 points. So out of n points, we will have to do NC2 combinations, and for each combination, then we have to match whether that line fits which of the data points and so on. So NC2 will be basically an order of n square number of points, and then comparing with each point again will give an order of n cube combinations. So that will be little bit computationally exhaustive. So it is not a feasible method to do that. So we are trying to find some better methods which are more faster and which are more robust. So voting is also kind of a way to do it more quickly. The thing is, as the name suggests, voting, we are all familiar. We are in a democratic country, so we all do cast our votes to select leaders or different peoples at different point of time. So the idea is same here in computer vision. In fact, voting is one of the common thumb rule that we do whenever we are not confident about a result from one source of information. We would like to combine multiple queues and then use a voting, basically the majority so if there are, let us say, n number of queues or n number of what do you say evidences, so for a particular decision to be made. So, and if there are different decisions which are being arrived at while we are combining those evidences, so we see which one got the maximum account of the evidence. So that decision we take. So that is a general method, because generally in computer vision or in any machine learning or things, it is not good idea to rely on just one evidence, or so it is always to have a more robust thing, be better to have multiple sources of informations and try to combine them. So we'll see this general idea later on also in other applications when we talk about, but this is the first application that we are talking about here now. So what we will do here basically, that we have our data points basically. So we'll let each those data points, we are calling them features here because we are talking in the context of features. We'll let each of those feature points cast a vote for all models that are compatible with it. So for example, a single point when we take, there can be a family of lines that can pass through that single point. So we are going to cast, so that single point will cast vote for all those points that can pass through it. And then similarly, we'll have another point, let us say it will also cast votes for all possible set of lines that it can basically, that can pass through it, for example. So we'll do this for all features, each of them casting votes for a particular set of line or a particular set of model parameter in general. And then at the end, after all casting is done, we'll look for that particular line or basically that particular parameters, because line can be defined by two parameters, slope and intercept, y0 to mx plus c. So our parameters are just slope and intercept. So we'll look for those values of m and c basically which receive the maximum votes. If we are only, for example, if we are only know that there is only one line in the image, or we are trying to find the largest, the lengthiest line of the max, then we will look for the one which got the majority of the votes. Or if we are willing to find if we know there are many number of lines, then we can put a threshold and say all of them which are above the threshold votes, they will be basically, they are all valid lines. So that is what we are going to do basically. And why it will work? Because the problem is that we want to tolerate outliers. We are saying that our basically, let me change the color of the, sorry. So our goal is to tolerate outliers. Our goal is to tolerate outliers. That is while fitting the models, we have to be very sure that outliers don't disturb our model fitting. Any noise, random noise, or any data which is missing, they all should not basically cause problems for our. Do not do a random fit. So why voting will be robust to these things? Let us try to understand. So there may be noise and clutter features available, and they will also cast their votes, but typically their votes would be inconsistent with the majority of good features. So we are assuming that majority of the features are good, outliers are going to be minority, and even if they are going to cast vote, first of all they will be in minority, and then even if they cast vote, they will cast for some random model parameters. For example, in our voting scheme, we have a nota, none of the above. So if you are not satisfied with any of the valid candidates which are really contesting the election, you press nota. So the noise features are going to basically cast vote for some one of the random things, and multiple noise features are not going to basically be consistent with the same model. They will all cast vote to some random parameters. So they are not going to, those random votes are not going to increase. They are never going to become a majority count. Only the ones which are really falling on line, they are only going to vote consistently for that single set of line, or for that single straight line. So the ones which are really existing, those are going to get the maximum counts, whereas outliers are going to do some random votes, and they will be basically anyhow discarded, because at the end we are going to count the majority votes. So, and this also will be able to handle if there is some occlusion. For example, if some of the features are not observed. So, so if we are having a straight line, or if we are having a circle, say let us say some part of the circle or some part of straight line is occluded or not being visible, still because the majority of the thing is visible, So you still you'll be able to get a good number of count for from the remaining features, because we are doing a global voting. It's a global optimization method. So even if part of the things is broken, if part of the straight line is broken or inconsistent or basically occluded by some other things, still you the majority of the remaining part will be able to give a good count. So is that clear? Does it make sense why voting will work, will be robust against outliers and noise and problems of occlusions that we find in real life scenario? Anybody has any question on this?
Excuse me, sir.
Yes, Gaurav.
Yes, sir. So, like, to summarize what you have mentioned,
Mhm.
the features which are like, say, which are not noise, they will be consistent because they will be sharing some specific attribute or some specific behavior. However, the noise, they will be chaotic. They will be very much random. So that's why their votes will be very much random in nature, and hence they will be essentially ignored.
Yeah.
And the main features that we wish to have, because they share some sort of similarity, that's why their votes will matter and they will be retained.
Correct.
Is this the point,
Yes,
sir?
correct. You're right. So let me just elaborate more on this. So when I say they are consist, so let us say these are some, maybe I should not have drawn the line. Let us say there are these feature points. So most probably there is only one line here, and then there are some outliers like this. I should have taken a different color, but it's okay. So these lines, these points, they all are going to vote for this particular value of slope and this particular value of intercept. Whereas all these lines, they may vote for some random lines or something like this. And they are only going to, for this line only, for example, for this line, there is only this one point is going to give one vote. None of these lines may probably give a vote for this line. So all the random points will not will even they may also cast vote, but their vote will be to some random things, and it is very unlikely that all the outliers are going to basically cast a vote for a particular random line. So I hope that point is clear. So the ones which are really existing. So if there are, for example, there are two lines really existing, then only those two sets of lines will get a real count, and all other random things, they may also give vote for some other line, but because none of the other points are going to vote for them, those will be suppressed. Those votes will be basically suppressed. They will be in minority, and the actual points which are really forming a lines, they are only those. So let us say this is y is equal to m dash x plus c dash, and this y mx plus c. So the votes, those points which casted vote for m and c, and those which casted votes for m dash and c dash, they will only be they will only accumulate and become a significant amount, whereas other things will become almost negligible. So let me just go through this implementation, and I think it will become more clear. But I think you have got the major understanding that whatever you express is okay. So again, we are using starting from a simplest case lines, but we'll see we can extend it to other arbitrary shape because it is more easy to understand through lines. So for example, when if you have to fit lines in this image, for example, this is probably an ATM machine or something. So there are many. So if we do edge detections, uh, so there are many lines which are basically possible, which will come out. And let us say we want to detect all those lines basically, and so on. So let us say this is the result that we want. So so how can we do this? So for this we have to answer basically, not only we have to detect a single line, but there are multiple lines. And if you want to also keep track of, so ideally our algorithm will just give the parameters, what is the m and slope. So we will be able to draw the entire line passing through the line to the image. But let us say we don't want it to draw the entire line, we only wanted to draw that this particular set of line, or this only those points which actually lied on that line. Then we could also keep track of that, which points belongs to which lines, because while voting we can have some additional metadata information, that okay, which point which edge location or x comma y location were actually casted a vote for that particular line. So once that line is selected, we'll just go back and find out which are the points which actually voted for that and draw a line only passing through them. So that way we will be able to not only fit multiple lines but also determine which points fit actually belong to that line and so on. So the idea of Hough transform is basically, again, that we have already told. First of all, we'll do edge detection. We'll take the image, we'll do an edge detection using a simple canny edge detector or whatever. And now these edge points are like feature points for us. So we'll take each of these edge points and we'll make them cast a vote for the compatible lines. So each edge point will cast vote for all possible lines that are compatible with that particular point. And at the end, we'll look for lines that get many votes. So how it will work, let us understand the mathematics and the algorithm behind it. So for this, we'll have to work in two space. One is our image space, our standard image space in spatial domain. Let us say we have x and y coordinate in two-dimensional. And let us say there is an image, there is a line in the image where you have found out the edge points. And that let us denote it by y equal to m naught x plus b naught. So that line has a particular parameter of slope m naught and intercept b naught. Okay. So if we see a corresponding parameter space, which we call it Hough space, because this idea was first proposed and patented by I don't know whether he was a mathematician or he was a computer scientist or whatever, by a person named Hough. So the thing is, the technique comes out from his name. So basically, it is a parameter space. So here our parameters are slope and intercept. So we'll have a parameter space. There are two parameters, slope and the intercept m and b. Okay. So this particular line has a particular slope m naught and a particular slope m naught and particular intercept b naught. So this is going to basically, maybe let us say m naught is somewhere here. I think it's not written properly. Okay, so this particular line has a particular slope m naught and intercept b naught. So in the parameter space, this line will correspond to a single point, which is basically m naught comma b naught, isn't it? And so a line in the image will correspond to a point in the Hough space. I hope everybody understands that. Now let us say try to write in I rearrange this equation. Let us say we have a single point here of x naught comma y naught. Okay. And from this line, this point, there are many possible set of lines that can pass through, isn't it? There are a family of lines that can pass through. Each will have its different slope and intercept, isn't it? So if you see our lines equation, we are considering right now a particular point x naught comma y naught. So that is fixed, let us say, because we are talking about a particular point x naught y naught. So x naught y naught is fixed, but m and b is variable. M and b will represent depending on which line we are talking about that is passing through this line. So this equation is referring to a family of lines that are passing through that point. Now we can rearrange this equation as this, isn't it? We can write it as b is equal to minus x naught m plus y naught, which is again kind of a straight line equation, but now if we look it into a parameter space where m and b are the actual coordinates or the actual variables. So so in parameter space, if you want to draw this line, it will be a straight line equation with a slope of minus x naught and an intercept of y naught, isn't it? So this will basically represent a straight line equation in the parameter space with a slope minus x naught. So that's why this direction and an intercept of y naught. I hope that everybody understands that now. So now a more interesting thing comes. So there is a duality here. If you have recognized the duality, a line in a image space corresponds to a point in a Hough space, whereas a point in a image space corresponds to a line in a parameter space. So there is a kind of a dual relationship between the two parameters, between the two image space. A line in one represents corresponds to a circle, a point in another, and point in another one corresponds to a line in the other. So I hope that everybody understands it. So far that was the thing, but how it makes it interesting is this. So let us say now if we take 2 points x0 y0 and x1 y1, so those 2 points will correspond to two different set of lines which will basically intersect at a point. So now if you want to if you want to know which if so these 2 points are going to define a unique line that passes through these two lines, through these 2 points, isn't it? So 2 points can define a straight line equation. So if you want to know what is the slope of this line, how we will know that? By looking into the parameter space. How we will know that line? Anybody has idea?
So we can solve because we have the values of x1 and y1 with us, and basically we have two equations, two variables in the Hough space. So that can be easily solved with the matrix transformations.
So by
that will provide us with the B and M value using which we can draw the line in the image space.
yeah. So but visual from the perspective of understanding the analogy here. So when we try to solve these two equations, what we are coming at? We are coming at this. We are basically coming at finding the intersection point. So the point where these two lines meet, that point will correspond to this line, because we had said that a point in Hough space corresponds to a line in the image space. So the intersection point of these two lines in the Hough space will correspond to the straight line equation there. So the slope value here and the intercept here, that will define the straight line equation in this case, isn't it? So that is the basic idea, basically how we now that will help us to understand that will so using this basic idea, we have came up with our algorithm like this. So what we will do is basically, let us say we have multiple edge points in our image space. So each edge point will basically vote. So we'll have a parameter space which we will keep like an accumulator, basically kind of a 2D matrix here. Okay, so sorry. Okay, so what we'll do, each point here will probably correspond to one line here, another point this will correspond to a line here, and so on. So each point here will cast a vote for all the bins in this. So this accumulator space, if we divide it into bins, so we'll quantize it. So we will basically increment m by a fixed value, and similarly we will increment b by a fixed value. So we'll quantize it and we'll create bins in this accumulator space. Okay, so now each line which is basically corresponding to a point in the image space is going to cast a vote for all the bins that it passes through. Similarly, another point here will cast a vote for all the bins that are passing through it, and so on. Now all these points probably, because they will be they are basically kind of a best fit line is like this somewhere here. So they will all so this particular bin is going to get the maximum count if all these counts are at the end are counted. So probably this may have just one, this may have just one, this may have one, and so on, but this will have at least 1 2 3 4 value, isn't it? So at the end, if you see the majority votes, we'll know that this is the intersection point for all these things, and this is the equation this is the straight line equation which is basically passing through all these points. So we'll accumulate votes in discrete set of bins, and the parameters with the most votes indicate line in image space. So now that depends whether we are only interested in finding one single line or multiple lines. If there are multiple lines, we'll have, instead of just picking the majority vote, we'll have to make a threshold that any votes which is larger than that, or basically we'll do another way to do that. We'll count the majority number of votes or the largest number of votes, and from that we'll be able to figure out multiple lines. Is that idea clear? Is the basic idea of the Hough algorithm understandable, or if anybody has any question, you can ask now.
Excuse me, sir.
Yes, Gaurav.
Yes, sir. So as compared to the earlier slide, what we are doing over here is, say for instance, we have 4 points in the image space. Now for each of the points in the image space, what we'll try to do over here is basically try to draw a line in the Hough space so that the equation that you had mentioned for the Hough space becomes satisfied. So let's say we are varying v and m over discrete values, as you had mentioned, again and again, and there will be one specific v and m value for each we can say point, which will satisfy the line equation in the Hough space. So with that, we can say that each point in the image space will correspond to a line in the Hough space, and after the end of the algorithm, we will be say solving more than one number of equations simultaneously in order to obtain the common point.
Yes.
That
Yes, you are correct. So again, let me just explain it a little bit more. Anyhow, that is covered in the coming slides, but because you have asked it, so let me explain some more details of this. So yeah, a single point is going to will correspond to a line in the Hough space. So what we'll do, so let us say we have decided m is going to vary from 0 to some value and b is going to vary from 0 to some value, and we have discretized it. So we are going to increment m from 0 to all these possible values. Let us say we are incrementing by 1, just for sake like this. So we are going to vary value of m from 0 to whatever maximum value, from minimum to maximum, and then from this line we'll get the value of b. So so that way we'll know which are the bins where this line is passing through, and we will we'll increment the count there by 1. Similarly, for another line, we'll have another value, another set of bins will get vote casted, and we are going to keep on accumulating all those votes. And at the end, those bins, we will look into those bins which get the maximum vote. So I think that would have made it more clear. But anyhow, we are going to come to the algorithm, so that will make it more clear. But before we write out the formal algorithm, there is one issue with this line representation that we have already also seen in the least square methods. For vertical lines cause problems, especially if you're writing line equation in this form, when we have to deal with lines which are almost perpendicular or vertical. The slope of those lines tends to infinity, and if we have to a kilometer space, if m tends to infinity, how will we represent that 2D matrix in our practically in our algorithm? Because if m is going to take a very large value, your space, how will you represent it? That will become a problem. So to avoid those things, a slightly different representation of line is used. It's not exactly polar representation, but what basically it says is, it's like we are still working in Cartesian coordinate xy, but using the basically unit vector which is perpendicular to the line equation. So this is your straight line equation. Basically it can be written as ax plus by is equal to c or something. So instead of writing it the general ax plus by is equal to c, using the normal unit, using the perpendicular and making it a unit vector. I hope you would have come across this way of writing a straight line equation somewhere in your calculus or geometry somewhere. So I'm not going to explain how equation comes, but I hope everybody would have come across some point or the other, and you can refresh how this comes. So this way you can write a equation for straight line as x cos theta plus phi sin theta is equal to t, where theta is the angle which is making which the perpendicular to that line is making from the x-axis. Okay. So, and d is the perpendicular distance from the origin to the line. So this is also one other way of writing our straight line equation using the perpendicular distance and the theta that the the normal vector of to the straight line makes with the x-axis. Okay, so now the advantage with this is now we have avoided the problem of slope getting infinity. Now we will represent now our instead of m and b, our parameters are theta and d. So now instead of m and b, we have the parameters are theta and d. Theta is the angle that the perpendicular makes with the x-axis, and d is the perpendicular distance from the origin. Okay, so the parameter space will become slightly different, and so there are multiple things here. So now no more that same correspondence will be there. A point in the image space now will not correspond to a line in the Hough space. Rather, it will correspond to some kind of a sinusoid, because now we are having cos and sine values here. If you see, so a point in the image space will correspond to some kind of a sinusoidal function in the Hough space. And but the good thing with this is the theta and d can be now easily restricted to some finite values. So for example, if you have an image, let us say you have some image. Okay, so depending on where you decide your center can you can decide at the center of the image or at the top left corner or whatever. So depending on that, now the theta values can either range from 0 to 360 2 pi, or from minus 90 to plus 90. So if you are having theta, so it can either range from 90 degree to minus 90 degree, or it can range from 0 to pi, and so on. And similarly, the d value can range from 0 to the maximum diagonal value, which is the maximum distance in an image, and so on. So now we'll have a finite limit from the for each parameter, from some minimum to some maximum, and that finite limit will depend on what is the convention that you use. So we'll see that in a second. So one thing, this is what I said. Now a point in image space will be a sinusoidal segment in the Hough space. So I don't know whether I have an image here. I will see that how this sinusoid looks like later on in the thing. So now with this new modification, the algorithm will look like this. So we'll have our Hough parameter, which is base Hough space, which is Hough accumulator, which is nothing but a 2D matrix, and we'll initialize all of the values to 0 in the beginning. Now what we'll do for each edge point, because we'll not directly take the raw pixel, we'll first detect edges, and then wherever we have found edges in the image, for each edge point, what we are going to do. So in this case, for example, we have decided our theta is going to range from minus 90 to plus 90. So theta is going to range from minus 90 to plus 90. Okay, so that we have fixed. So our bins theta will range from minus 90 to plus 90, and we can use an increment of 1 degree, 89, 88, 87, and so on. So that way we can have some quantization. That depends on how fine you want to do. But we'll have to run a loop for all possible values of theta from 90 to 90, and then calculate the corresponding d value using this equation. Now in this equation, d can be negative, because theta is having plus value and minus value also. So sine theta and cos theta they take plus value and negative value. So d can come out to be negative, and that may also happen because if you are choosing a center somewhere here, so d can, if you go in this direction, d will be positive. If you go in this direction, d will be negative. So that is one way. If you want to restrict d to positive only, then you will have to range theta from 0 to 360 degree. So that details I leave it to you to read from the book later on if necessary, if you have to implement it. But the idea is basically we'll have to vary the theta from some minimum to some maximum, get the corresponding perpendicular distance, and then for each pair of the theta and d, we will increment the count for the Hough accumulator. So the accumulator will increment the count there, and at the end when we have done for each edge point, we'll find the values of d theta where this is maximum or near to the maximums. So if there are multiple lines, we may decide, okay, 80% of the maximum value for all those bins which have got about 80% of the maximum values, they all will consider them as a valid straight line. Or we'll have to have some threshold beyond this. If it is beyond this or less than this, we'll consider it, otherwise not consider it. So that way we can, sometimes we may have to also do a non-maximum suppression, because we'll see it's because of error, because of outliers. Sometimes the noise points may not be exactly lying on the straight line. So they may not all cast vote for a single bin, although they may all be falling on the same straight line, but they may happen to cast vote to nearby bins. So we'll have to then do a non-maximum suppression also. And so all those details I have not written here, but just to make the algorithm a little bit simpler. And finally, once we know that d and theta, that is your maximum, we have already found the line. So that is your algorithm, basic Houghtransform algorithm. So how good it is? Let us try to understand its complexity. So in terms of space complexity, it suffers little bit badly, because it depends on how many parameters you have, how many dimensions. So if you have, in this case for straight line equation, we have 2 dimensions, m or intercept, or d or theta. So the total space requirement was basically, and if you have k bins, so let us say each bins is quantized into, each parameter is quantized into k equal intervals. So now k square was the space requirement for the straight line problem. But if we have some arbitrary parameter where the number of parameters are more, let us say if there are n dimensions and each dimension is divided into k bins, basically, then we'll have k to the power n dimensional space that will be needed, or basically k dimensional or n dimensional matrix will be needed, each of length k. So the total requirement will be k to power n. So that is little bit problematic, not so much problematic, because space and memory, nowadays we have a lot of memory. But the problem is when we have more parameters, the algorithm accuracy, the algorithm suffers, because remember, even in machine learning or pattern recognition, you may be studying this. When we have a smaller dimension and we have some feature points, classification is accurate. But as the number of dimensions increase, and unless we have huge amount of data points, the classification will not do good, because they become very sparse. As we increase the dimensions, they becomes very sparsely located, and classification becomes a difficult thing. So that's why we go for PCA and all those things. Similarly here also same thing. If we are going to increase the number of dimensions, our total space is going to exponentially explode, and the accuracy suffers because of that. So it is only good as long as we have fewer dimensions, maybe 2 or 3 maximum. Beyond that, Houghtransform may not perform as well. But the time complexity, it is a very good thing. It is a big plus here, because what is the time complexity? Earlier, for example, in the case of straight line equation, if you have to do a brute force approach, our time complexity would be order of n cube, where n is the number of points. But here the number of, we have to only do for each edge point, and we are basically running a loop for each edge point. So it is directly proportional to the number of edge points, which is basically order of n. Of course, there is small loop here, but that loop is also fixed, k bins. So maybe we can say order of k into n, where k is a constant. So the real variable is n, but instead of n cube, we are basically having proportional to n, which is the number of voting elements, which are number of your edge points. So time complexity wise, it is very good. It is very fast. And of course, we are able to fit multiple lines and so on. So we'll see, if time permits, we'll show a demo, but let us just see how it performs so how it looks like in the Hough space with these sinusoidal things. This is what I say. So if you have a straight line, each point is going to basically vote for this kind of a sinusoid. So each point is going to basically vote for a sinusoid, if you see. something like this. So that is what will happen. So, and but finally they will all the majority of the vote will come at this point, which is the bright point. So if you visually see this as an image, so bright value will represent high vote count, and black or will represent no votes, and lesser value will represent lesser votes. So you have to find the peak values, or you have to sometimes do a non-maximum separation to find the exact peak location. So for example, if you have a square in your image, so there will be 4 lines, and your Hough space will look something like this. So you can see there will be distinct 4 peaks, which will correspond to these 4 lines, 4 sides of the square. This is again a block scene, which is some random scene, but it has some straight lines you can see. So all these, that's why you will find that. So probably this is the longest length, so this has the maximum count. But then we also see some other bright points where they are there, which will basically correspond to the smaller line segment, and so on. Now, how it performs, how is the noise will affect our Hough voting. So let us say, as we said, our images, our edge points are not straight or not on the straight line. They are a little bit Gaussian noise is introduced. Let us say the points are a little bit shifted here and there. So all of them are not falling on a straight line. So if you do a voting, as we expect, they will not all vote for a single bin, but they will vote for a neighborhood of that bin, and then we'll have to basically do a non-maximum separation to find the exact or the best fit line. But still, it is robust to do that. It is not a problem. It will be able to handle this kind of a noise. But if the noise is totally haywire, it's not a Gaussian noise, but of course, there is no straight line here. If you see that, then if this kind of a noise happens, then there is actually no straight line here, unless maybe some few lines you can say, okay, these may form a line and something. So you will have a random votes, and probably it will be very difficult to pick out a distinct peak. So if you have a huge noise, of course, there is no point in fitting a line in this kind of an image. So Houghtransform will also not be able to give it's not going to give a random answer. So you will have, because most of these peaks there will be huge many peaks, and most of these peaks will be almost similar. So there are some extensions that you can make it to make it little more fast and perform, be more robust. We'll talk about some of the extensions later on, but one extension I'm going to talk here. Most of this time, this is what people end up doing. Instead of varying theta from -90 to +90, because that is also a little bit more expensive, we can use some idea here. For example, if you have a straight line, then for at each edge point, because we are already calculating gradient before we calculate edge. So at each edge point, not only we have the magnitude, but we'll also have the edge direction, the theta direction, isn't it? So we also have the edge direction. So so that means if we are going to cast a vote for a particular edge point, we don't need to cast it. So for this point, let us say we don't need to cast for all possible random values of theta, because the straight line is going to will be almost along the edge direction. So once we know the theta, the gradient direction, we are going to know that that is going to be the straight line along that theta, or maybe little bit around theta. So instead of exact theta, just to be a little bit tolerant to the noise, we can decide, okay, maybe plus minus 10 degrees from that theta, but we don't have to do for the entire span and for the entire -90 to +90. So once we choose the theta we'll get only one particular d for that theta, and we'll give it count. So it will speed up your algorithm much faster now. And so the only difference is that instead of having an inside for loop, we have used the theta, the gradient direction also in our algorithm. So which basically speeds up the algorithm. Later on, see, this also helps us to reduce the dimension also sometimes. Any question till this point before we see how we can be extended to circles? Has everybody understood how this Hough transform will work for straight line at least? I don't think we have time left for circles. So we'll discuss that in the next class, tomorrow's class. So let me just ask for questions if anybody has a question till now.
Excuse me, sir.
Yes, Gaurav.
Yes, sir. So is it natural to apply the Hough transform on the entire image, or is there an approach like say you divide the image into smaller neighborhoods? Say, for instance, if we have some n by n image, then you divide it into say some 4 by 4 sort of neighborhood, and then you apply the Hough transform for each of the neighborhood. Is there any sort of approach present, sir?
But why you want to do in a local neighborhood for some reason?
Yes, sir. So what I am thinking is that if we consider the entire image as a whole, then it may so happen that there's very less probability for this. However, the noise components or the noise feature points, they may actually turn out to form some sort of line. However, this is because like this is you can consider it very similar to say to the law of large numbers, where because we have something in very much something of less probability in very huge numbers, you tend to see a greater effect of it. So similarly, because we have the entire image in we are scanning the entire image in one shot, so therefore even though the probability is less, but still we might be able to see a line that is full of the noise components. However, in a small region, there may not be presence of any such line.
Yeah, so there are two things to this actually. First of all, as you said, we are not doing for entire image. We are first doing edge detection. So already we have reduced our data points to very few points. And then again, as we said, it's very unlikely, even if that most of there may be huge number of random points, but they will all not vote for us for the same model. They will vote for some random models, so for some random straight line. So it's very unlikely that a single straight line is going to get a good count by all the random points. So that is a very extreme scenario that may happen, and if that is happening, probably that is the line there. So we don't have to really worry about that. So for example, in this case, if accidentally all these random points were actually lying on a straight line, probably then Hough transform should give that value. So I don't think we really need to. Another problem will be once you have divided into local things, then how do you combine them? Then you have to think about the additional step of the algorithm by how do you combine them, how do you take into account the local votings in the global sense, because the whole thing is we want it to be in a global sense rather than a local. So the Hough transform is kind of a global mechanism uh, to do the data fitting. So if we do local data fitting, then later on we have to think of ways how do we combine those local fitting to a global fit. So that becomes a little bit problematic. And for local fitting, although anyhow we have other methods, so if we have to refine it, we can use those local fitting methods that we already discussed during SIFT, for example. We can use matching and all that in the local region to figure out whether it is a correct match or it is just a random thing. So we can, for those things, we can instead of modifying Hough algorithm itself, we can use other techniques to do a further refinement. So that will be really more easier, I think, rather than modifying this way. But we'll see some extension. What you're thinking, maybe in slight direction, some extension of Hough transform do basically. So they try to do binning little bit more coarse. So one thing is instead of doing a fine bin, we can do a coarse bin. So that trade-off we'll talk about later on in tomorrow's class. So some modifications are there to handle little bit the problems like here and there. but I have not seen this this way of applying Houghtransform anywhere, where they divide it into sub image into sub part and do a separate accumulation for each look for each sub image separately. So I hope you are satisfied with the answer.
Yes, sir. So also just one more question. The later on method that you mentioned, it was like the sine wave things. So that becomes a bit non-intuitive as compared to the original, what you can say, the original Hough space line thing. So the main issue over there was that we cannot handle the vertical lines.
Yes.
So fitting
vertical or near to vertical, because near, as soon as you go near vertical, the slope becomes exponentially large. So when slope becomes very large, your space, how will you define the space? Your m may start from 0, but what is the maximum limit that you will keep? There is no fixed limit that you can decide what is the upper bound that slope can go. So how will you fix your accumulator space? That becomes a problem.
Yes, sir. So just regarding that, let's say that we fix him to the slope to some specific value,
okay,
and let there be some specific output that comes out. Now, what we do is basically we threshold the result, as in all the vertical lines, they might be giving us some value that is above some specific set threshold. So with that, we can eliminate the problem in that area. Can we do this, sir?
It will be difficult logistically. How first of all, how will you detect vertical lines?
Yes, sir. So as you mentioned, that vertical lines tend to have a very large amount of them. So in that scenario, what will happen is that the value of m will keep incrementing on, and it will eventually hit the limit. And with that specific, with highest value of m, we will be having some sort of output of b. So I'm talking in that sense.
No, but we'll not be able to figure out those values of high and values of m, because we have not represented the Hough space. So how we are going to determine those values of m, even if they are very high? How will you calculate that? Algorithmically, how will you calculate that? Because there is no voting done for those values. So, and anyhow, this it may look unintuitively, but you're practically, in terms of implementation, there is no change. You are still doing accumulation. You're still doing. You don't have to visualize this. You have to just, at the end, you have to just see the maximum value. So whether you are using a straight line or you are using this sinusoid, at the end you are only going to count the peak values in both cases. So your implementation step does not changes any such. Only thing is, while implementing, you are, instead of using ax plus b, you are doing just x cos theta plus y sin theta, and you don't have to do, the computer has to calculate that, so you don't have to worry. So in terms of your code, if you have to write the code and all that, the code is not going to change anything. Only probably this line is going to change. The steps remains the same. So it may look non-intuitive to you, but in terms of visualization, it's not so non-intuitive as such, as I feel. But yeah, if you don't have to visualize this as anyhow. At the end, you will have to, the algorithm remains the same. Only thing is, only this calculation changes. Other steps will remain the same. So why to complicate things? This is a more easier thing to do than the other way. Okay, so next time we'll discuss about circles and some extensions also in the next class. So we'll take the attendance and then close the session.